we're back, and this is going to be our section on applications of quadratic modeling. And hopefully in your next math class, you take this to the next level and you talk more about projectile motion and how that's really truly modeled. But for today, we're going to stick to the basic quadratic functions. Now, the original equation that is on our notes here, this is a very American equation. It's h equals negative 16t squared plus, this is called v sub naught, meaning initial. Anything with a 0 subscript means initial. V sub naught times t plus h sub naught. So let's define some of those variables. So the h that's at the beginning of the equation is the height, and I should say the current height, or the calculated height, I suppose. T represents, I'm sure you guessed this, time. And the unit on time can change depending on the problem, so you do have to watch your units a little bit. So in this particular formula, the v sub naught, it stands for initial velocity, always. But as far as labeling goes, velocity is kind of like, speed. So because we'll talk in a minute about why, but this is going to be feet per time. And then h sub naught is the initial height. So for a lot of these problems today, they're going to have an initial height that they start at. So whether it's being kicked or thrown or launched or dropped, there's an initial starting height. And then we're going to see a quadratic function. It's going to look like that when we graph it, and it's going to be coming down because anything that gets launched or kicked or thrown or dropped, on Earth eventually will hit the ground or whatever is it considered its base level or its ground. So, sorry, I'm doing that thing where I check my phone in the middle of my lesson. That's pretty rude, right? All right, so let's talk about this negative 16. How did I know this was a, quote, American problem when I saw the negative 16? Well, that is referring to the acceleration due to gravity as it is measured in feet per second squared. So because our problems are like on the way down only, my physics friends out there are like, wait, it's negative 32 feet per second squared. It's on the downward trend of the parabola, so it's half of that, right? So negative 16 is all about gravity. That's going to be constant in all of your problems here that we're going to do. So it is the acceleration due to gravity. And then because this particular problem was designed for a U.S. citizen to do some calculations, because we typically, as we're doing these problems, measure things in inches and feet and the English measurement, I guess. The rest of the world doesn't, because it's a really weird way to measure. The rest of the world measures in metric, and if you're measuring in metric, then this initial value gets changed to negative 4.9. And that would be meters per second squared. So gravity, that A value for these formulas is negative 16 feet per second squared. And then, so I should make a little note here, the time should be measured in seconds. I forgot about that for a minute. So the US problems is negative 16 feet per second squared. In the metric problems, which I do throw one in on here, it's negative 4.9 meters per second squared. So this very tech heavy lesson here. So you want to have a graphing calculator, either the emulator on your Chromebook handy, or you can pull out Desmos and use their graphing calculator, or if you have your own, that's great too. But we have a rocket that is being launched at an initial velocity of 45 feet per second. And a platform, the original height of the platform is 70 feet high. So it's being launched and then it's going to come down. And there's the equation. So for our regular Algebra 2 class, I'm going to be giving you these equations primarily, and then you're going to be using it and interpreting some of the key features. So here, instead of, usually we saw an H on the last screen, H equals, well, they're saying S of t. So like, what does S of t mean? Well, that's the common notation for position in physics and in math classes. So the current position of your ball or your arrow or whatever what are we doing here? A rocket. So I should be able to figure out the position of the rocket at, 1 second, at 1.4 seconds, at 3 seconds. Seems like something important, right? So yeah, we have to do some calculations there. First question is just a look and see question. What's the initial velocity? Well, the initial velocity, remember, is the coefficient in front of that middle term. So the one that just has the t. So the initial velocity is 45, and I know it's feet because it's got that 16 in front, so feet per second. Remember, velocity is kind of like speed. So like how you measure miles per hour, it's distance versus time. What will be the object's maximum height? This is where I start using the calculator. So I go to my calculator, and I have to type in this guy, which I'm going to totally remember. Not. -16. I have to use x because of the mode in my calculator. All right, I already forgot it. It was 45 and 70. All right, plus 45x plus 70. Now, to find the maximum, I'm going to need to graph this. That's the best way for you to find the maximum. And I can tell you right now, my window is not going to be appropriate because my window is the standard window and only goes -10 to 10. So let's think about this. X is measuring time. First of all, I'm measuring 10 seconds before I even start the rocket. Like, dumb. Why would I do that? And then I'm only going 10 seconds into the future. I don't know a lot about rockets, but I feel like they're in the air for longer than 10 seconds, even like little toy rockets, but who knows? Now, the Y's are measuring the height in feet. So what I'm seeing is -10 feet below the ground and then 10 feet up in the air. But remember, we started the rocket 70 feet up in the air on a platform and then shot it upwards. So this is clearly not a good window. The first thing I'm going to fix is I want my time to go from 0 to, I don't know, I'm going to kind of guess and say 30. We'll adjust it if it's not right. So 30 seconds out. I think that'll be okay. Now this seems weird because I usually don't like negative numbers for windows, but for height I do because I want to see like the line where the ground is. I'm going to leave my Y minimum, my minimum height at -10 just so I have a little bit of cushion in the ground. But we got to go way bigger than 10, right? So again, I'm kind of guessing. I'm just going to go to 200 feet in the air and hope for the best. So now when I hit graph, I was way generous with my time, apparently. So I'm going to go back to window. I didn't mind the height. I could have brought the height down a little bit, but I don't need to go 30 seconds out. Apparently 10 seconds would have been fine. And if I was smart, I would have just kind of peeked at the window before I went and messed with it. Oh yeah, this is a real dud of a rocket, let me tell you guys. So this is the rocket being launched and then eventually hitting. So the question was, what was the maximum height? We need to find this part of the parabola right here. In order to find that, we're going to go to what's called the calc menu. It's right above trace. So go second trace and then choose the appropriate one that makes sense. We're going to find a maximum. So choose maximum, number 4. So I can tell that as far as time goes, it hits its maximum in between 1 and 2 seconds. I don't really know what the maximum is, but as far as time, it's between 1 and 2 seconds. So when it says left bound, I just have to give a time that is, so like here's 1 second, here's 2 seconds. I just have to give a time that I know is before that happens. So I'm just going to say 0 because clearly that's before it hits the maximum. And instead of scrolling, I just typed in a guess that I knew was before it. So now I'm going to type in, it says right bound. Now I'm going to type in a guess that I know is after it. And I'm pretty sure 2 seconds is after it, but I might as well go a little bigger. I'm going to go 3 seconds. Very much so. Okay. And when you do this typing of a guess and hitting enter, you don't have to hit enter again. It automatically submits it for you. You can't see it, but there's a blue line right here. So it says, do you have a guess? And maybe you do have a guess. Maybe you think it's at like 1.2 seconds. You can type that in, or you can just hit enter because you don't care. There we go. So this maximum right here, this ordered pair is 1.4, I'm around the 100th always on these, 1.41, comma 101.64. So I got to think about what this means, right? This is time, and then this is height or position. So the question was, what was the maximum height? And I'm going to write down 101.64 feet. Where'd you go, paper? All right, so let me write that down. What will be the max height? 101.64 feet. So just a rule of thumb, if it doesn't say where to round, I want you guys going to the 100th place. How many seconds have elapsed when you will occur, like at that maximum height? That was the other part of our ordered pair, which I already forgot. So 1.41 seconds. Okay. So on our calculator, I'm going to write myself a little note. So on the calculator, you know, we had one of these pictures. We had to find the maximum right here. This is always tricky when we have a really tech-heavy lesson. If someone's looking at our notes, like they don't really make sense, right? So on your notes, you want to write down as much as you can. And maybe I could be a good teacher and write down the rest of this. 1.41, and then, oh, except you can't read any of that. Try again. All right, so this ordered pair right here was 1.41, 101.64. Ah, you still can't read that. Oh, well. All right, so now this next part, oh, thank goodness for technology. It wants to know the height, the position of the rocket at exactly 1 second, 2 seconds, and 3 seconds. Well, you have a graphing calculator that'll do that for you. So I'm going to go to my table. I'm going to go to second graph. I'm going to erase all my ink. And I'm going to look. So here's 1 second, 2 second, 3 second. I'm just going to copy down these heights. 99, 96, 61. 99, 96, and 61. And I feel like I copied that wrong. So let me go double check. 99, 96, 61. All right. So this next question is the one that always stumps kids, so be careful. They want the average rate of change. Anytime you see average rate of change in math, and if you continue on in math beyond Algebra 2, you're going to see this phrase a lot. It's just a very fancy way for now of us just saying slope. So they want the slope from t of 1 second to 3 seconds. So if you specifically look at what happens at 1 second and at 3 seconds, they want you to find slope. So slope is the change in y, which I'll call the change in height, over the change in time. So for us, that would look like this. It would say, and you can go any order as long as you keep your order the same, right? So I'm going to say 61 minus 99 over 3 minus 1. And I should totally be able to do that in my head. So 38 over 2, which is positive 19, nope, negative 19, and the negative is important, feet per second. If you think about what you were measuring in those X's and Y's, this was feet and this was seconds, so feet per second. And that's important to the problem because that means your rocket between that time was on average dropping 19 feet per second. Again, I think about why these problems might be used. Yes, rockets are important, like literal rockets that go up into the sky and eventually need to go somewhere. Obviously, the formula gets more complicated when you have some other things to consider, but things to think about. Okay, so that was a launched object. What if we just drop something? So we still use the same formula. And this is measuring in feet, so we got this weird American formula. So this negative 16 t squared plus the velocity times t plus the initial height. Well, if you're just dropping something, you don't have any initial velocity because you're not throwing it. So like dropping it, the only thing that's affecting it is gravity. So that simplifies the function quite a bit. This number right here of where you're dropping it, this is the initial height. And that's kind of all you need to know. So for us to develop the function, the final height would be negative 16 t squared plus this 120. So that's the formula we're going to use. They want us to sketch it, which I transfer over to my trusty calculator for that. I'm going to keep that negative 16 part. And then I'm going to say plus 120. And then this is where I regret everything I just did because I usually screw up the overtype. Now, sometimes you luck out. And whatever your last window was, it works really great for this next problem. It's not a bad window, you know? Like, I'm okay with that. I'm just going to keep it. Beautiful. All right, so one major difference, and I don't know if I drew it very well here, but remember this launch object started at a height, went up, then came back down, as opposed to this object, which just started at the height and started coming straight down. So it's a little confusing to kids because they think that's the path at which the object is taking. That's measuring its position and its time. It doesn't mean it's floating out away from a building. It's just That's the way time is measuring across the x-axis. So they want to know, when does it hit the ground? What's the height at the ground? The height is 0. So the desired height here would be when you plug in a 0 for your h, this guy right here. So technically what you're setting up is 0 equals -16 t squared plus 120. If you're already using your calculator, just keep using it. Watch what we can do. This number right here, whatever it is, this is the thing hitting the ground. And I can see it's in between, you know, this is 2 seconds and this is 3 seconds. So it's 2.7-ish seconds. I don't really know exactly right now because I'm going to make my calculator find it. So on my calculator, I'm going to use that trace menu again, but this time I'm going to use the command that's called the 0 finder. It's where is the height 0 is what it's asking. So choose number 2 this time. Left bound, they want a time before it hit the ground. Well, for certain, 2 seconds was before it hit the ground, so I'm going to type 2. There he be. Okay, now it's going to say, give me a time after it hit the ground. Like, I'm really certain 3 is after it hit the ground, but just to be safe, I'm going to go to 4. And then you'll see these 2 blue lines pop up. The thing you're trying to find should be in between these 2 blue lines, which it is. So hit enter one more time, or you can type a guess. It's up to you. But you should probably erase this. There we go. Hey, good guess, Abruzzo. All right, 2.74 seconds. So what I'm going to do, because these are my notes, is I'm going to write a little note to myself here about what we did. We went to the calculator, and we chose second trace. We went to number 2, the 0 finder. And this does take a lot of practice because, like, yes, it is like a little computer, but you got to really think about what the command is asking. Left bound, right bound, they're asking a time before and a time after. They just want you to narrow down the window so they know where to do the calculus. That's what's happening, which is kind of cool. All right, so finally, a non-America problem. Right, so we're playing basketball in a European league, so we are measuring in metric now. We have the basketball is being released at a height of 1.9 meters. So this guy right here, I don't know why I crossed that off. This is your initial height. So that's where it starts. And then we have this initial velocity of 8.1 meters per second. So this is that v sub naught thing. And they want to know how many seconds till it hits the rim. And the rim, which I had to look this up when I wrote this problem because I didn't know, was a final height of 3.05. So using that model, but that modified version of the model, h equals, instead of 16, it's -4.9 t squared plus initial velocity times t plus your initial height. All right, let's plug her in. So for us, instead of writing h equals, I'm going to write 3.05 equals -4.9 t squared plus 8.1 t. And then our initial height, the ball release, was at 1.9 meters. Okay, so that's the model. What we're going to do now is we're going to use our calculator to help with the sketch. We're going to set this up a little differently, though. We're going to put one side of the equation into y1 and the other side of the equation into y2. All right, so there's probably no chance I'm going to remember this. I'll have to flip back and forth. So we had 3.05, which is just the height of the rim. And then, yeah, -4.9 x squared plus, I think it was 8.1 x, and we're using x again, not t, plus, yeah, I forgot, is it 1.9? 1.9. All right, so what you're going to, okay, first of all, the window from the drop a thing off a building doesn't make sense for this problem because we're just on a basketball court and we're not like launching the ball up into the air. So I'm going to have to go to window and I'm going to have to fix this. Now, I haven't played basketball in a long time, but I don't think I've ever shot a basketball that was in the air for 10 seconds. 10 seconds is a little ambitious, huh? So let's at least pull it back to 5 seconds. Now, as far as height goes, again, I never mind that you have a starting height at -10 because I think it helps to see below ground. But this is meters. So -10 meters is like -30 feet below ground. So that's kind of crazy. I'm just going to go not that. I'm going to go -1 meter below the ground. Again, max, well, it's meters. So like 5 meters would be 15 feet. I think that's plenty. I don't really think people throw the ball up in the air 15 feet, but maybe I'm wrong. And then let's hit the graph now. I think that's a great window. And I was even over ambitious with the 5 seconds because basketballs don't hang in the air for 5 seconds. All right, so this is where we need to transfer this to our paper a little bit. But what gets a little confusing is you see this parabola and the line intersecting twice. So you got this right. Whoops. I don't know what happened. I know what happened. I can't graph. Okay, so I think it was a blue line you actually had. And then we had this kind of shape happening. Whatever. Okay, so there's 2 intersection points. We got here and we got here. Which one do we want? Well, if you think about it, when you shoot a basketball, you arc, right? So you shoot above the hoop line and then it comes back down and it sinks into the hoop. So where it actually is going to hit the rim, or at least the level of the rim, would be this point right here. So while I'm on the screen, I'm just going to write myself a little note. We're going to go back to that calc menu, that second trace menu. But this time we're going to choose number 5, which is known as the intersection feature. We've used this before, I believe. So, calculator. I'm going to find this guy right here, which I'm guessing is like 1.6 seconds. I don't really know. So, second trace, this time choose number 5, which is intersect. And then enter, enter, enter. You don't even have to guess or do anything on that. I like the intersect one the best. Oh my goodness, I am on fire. This rounds up to 1.50 seconds. So how many seconds until it reaches the hoop? 1.50 seconds. That's a pretty good guess, right? And this is, this is a bit of a stretch. A lot of kids are looking at this problem going, I would never do this to solve this question. But it's nice to have the option, right? So the further you go in math, the lazier you become. And you're like, I could set up a quadratic equation, or I could graph it. Like, you're going to really love to graph things in the future in your math life. I just want to show you that we've had this problem before and we solved it algebraically. Or maybe not yet. I can't remember when we teach this to you, but I'm sure you've seen a problem like this. You can use your calculator to solve this. That's kind of amazing. So we know to find the area of a rectangle, you do length times width. So if I were to multiply length times width here, it would look like this. Length times width. And the area is 105 meters squared. So I'm just going to set that up as my equation. Now, if I was solving this by hand, I would now have to do some we haven't learned this yet. I'm sorry. I would have to distribute the x, and then I have to come through and solve the quadratic using one of my many methods that we're about to learn. But today I don't remember how to do that. Oops. And in the future, maybe I just don't want to do that because it feels like a lot of work. So instead, we're going to be lazy. I don't want to say cheat because you're not cheating. And we're going to use our calculator. So just like we did on the basketball problem, we're going to type one side of the equation into y1 and the other side of the equation into y2, and we're just going to see where they intersect. It's going to be great. You do have to play with the window a little bit. That is the drawback to using your calculator always. I already forgot the problem. I think it was x times 2x plus 1. I'll check, don't worry. If it's wrong, you're all screaming at me, I know. Okay, and then it equals 105. So on y2, I'll put 105. I thought I'd take a shot and see if it worked. The basketball window totally does not work. All right, so here's what we're going to do. I am trying to figure out the dimensions of a rectangle who has an area of 105. So I need to see where it crosses a height of 105. I'm not really sure about the 0 to 5 thing, but I know the height has to go way higher because it's got to hit 105. So I'm just going to go higher than that and say like 120. And I'm not going to mess with anything else. I'm just going to go wah. I do have to mess with something else. I didn't go far out enough. I need to go further out in the x's. So I'm going to go 10. So it's just adjusting our window one thing at a time. And now we're going to use that intersect feature. So second trace, intersect. And then I love intersect method. Just enter, enter, enter. Dunsies. All right, now notice the ordered pair. You found x equals 7 and y equals 105. This literally means x equals 7. So when they say, what is x? 7. This, remember, was the area. We already knew the area was 105. That's not like a big mystery, right? So if x equals 7, like our calculator just told us, now we can go back and find the dimensions. So plug in a 7 here, and obviously that's a 7. So 14 plus 1 is 15 by 7. What's the label here? Meters. Label, Abruzzo, label. I already can hear y'all way out there in internet land. You're like, Abruzzo, I just started making guesses. That's awesome. That would only work, though, if your dimensions were nice. What if your dimensions were funky or, at least not integers? What if they are funky decimals? Like, you want to be guessing for the rest of your life? No. And as your problems get uglier and uglier as you move on in math, you need many methods to get to the right answer. So using your technology, while it's not always appropriate, it's a nice backup plan. So yay for quadratic modeling. You guys need to practice this a lot. I'm sure I've given you some kind of cheat sheets of how to use your graphing calculator for the TI-84 emulator. And if you can't remember how to get that extension on your Chromebook, just contact me. But do remember that Desmos has another free option. I believe it's still free. There's lots of emulators out there, but you don't need to go and buy your own calculator. That's not necessary right now. All right, good luck, everybody.